Well, dear students, see this is the part of biomolecules, carbohydrates. We have two topic in this: carbohydrates and amino acids in biomolecules. So let's start this carbohydrate. Uh, See, as the name manifests itself, carbohydrate. Carbo means carbon, and hydrates means water. So basically there are so many definitions initially was made for to define carbohydrates. This is one of the definition, that hydrate of carbon are known as carbohydrates. This is one of the old definition. Similarly, one more definition will come into the picture, that carbohydrates are the group of organic compounds containing carbon, hydrogen, and oxygen, right? So one by one we should write also. So hydrates of carbon means carbon dot H2O. So hydrates of carbon. This is first definition. Second definition, what people define is that carbohydrates are the group of organic compounds containing carbon, hydrogen, and oxygen with 1 is to 2 is to 1 ratio. So the empirical formula for carbohydrates is CH2O. CH2O, right? And this is hydrates of carbon. Hydrates of carbon. Hydrates of carbon. So these are the two old definitions. After this, scientists found that some of the carbohydrate molecule have nitrogen as an element. So this definition or this definition is not sufficient. So finally, what this carbohydrates, how these carbohydrates are defined is, how these carbohydrates are defined. See, carbohydrates nowadays are defined. The latest definition of carbohydrates is polyhydroxy. Polyhydroxy means if any molecule, if any organic compound have two OH, minimum two OH groups, along with this, if it has aldehydic or ketonic group. So polyhydroxy carbonyl compounds, irrespective of other things, other may be present. This is the minimum requirement. So polyhydroxy carbonyl compounds known as carbohydrate. Other elements may present, but this is the minimum requirement. Polyhydroxy carbonyl compound. Carbonyl compound means may have this group, aldehydic group, and may have this ketonic, aldehyde or ketone. So and polyhydroxy means minimum two OH group, right? So this is the latest definition of carbohydrates. So carbohydrates are basically polyhydroxy carbonyl compounds, right? So as per this definition, if you see, this is the simplest carbohydrate known so far. See, and this compound is important as well. See, this is the simplest carbohydrate. How many carbon atoms are there? Three. One, two, three. So if the question is asked that the minimum number of carbon atoms, it means carbohydrates known with the minimum number of carbon atoms, so your answer is three. You know, this compound is very important, very popular, because this compound was known very early, and this compound is taken as a reference for capital D and capital L. How this, see, this compound, this carbon is stereogenic. So initially it was thought that organic compounds have only one stereogenic carbon in the initial days of the discovery of optical isomerism. So this compound was taken as a reference, and if OH group in the Fischer projection formula, proper Fischer projection formula means most oxidized group on the top and longest carbon chain on the vertical line. So if OH group is in the right hand side, then this is called D series, right? So in the relative configuration, although this is nowadays it is obsolete. Nowadays only R and S absolute configuration is in use, but in carbohydrate chemistry and in amino acids, still this D and L nomenclature is used. So this is called relative configuration, and we have two types of relative configuration, capital D and capital L, right? Capital D is not necessarily dextrorotatory, and capital L is not necessarily levorotatory. That's why it is distinguished capital D and capital L. If it is small d, then it is necessarily what, dextrorotatory, and if it is small l, then it is mandatorily or compulsorily it is levorotatory. But this has no relation. This capital D and capital L has no relation with the optical rotation, right? This D and L, these nomenclatures has no relation with the optical rotation, with the optical rotation. See, this capital D and capital N nomenclature is based on the, based with respect to this compound. This is known as D-glyceraldehyde, capital D-glyceraldehyde, aldehyde. And it is a reference for, it is a reference for this relative configuration, right? So if in future, if you have any group in Fischer projection formula have OH in the right hand side, then that compound belongs to D series member, right? And similarly, if CH2OH, and if in the Fischer projection formula this OH is in the right hand side, right? Or some more preferential group than this, if it is in the right hand side, then this is called and particularly in carbohydrate you will have only OH. If OH group in the left hand side, then this is the series of L series member, and this is known as L glyceraldehyde. L-glyceraldehyde. So D glyceraldehyde and L-glyceraldehyde, they are reference for, right, reference for this nomenclature. So in future, if you have drawn any structure for carbohydrate molecule, and in that molecule look carefully the second last carbon, see, first, second, third, you have to see second last carbon, not any carbon. Your carbohydrate molecule may have 4 carbon, 5 carbon, 6 carbon, but you don't see any other carbon, you just see second last carbon. So this carbon basically it is only 3 carbons, so this is the second last carbon. So the if the second last carbon OH on the right hand side, then this is the D series member. So I am writing some example here. Suppose that if you have a structure or compound like this, suppose that a compound has a structure like this. Now tell me whether this is carbohydrate or not. First, you have to decide whether this is carbohydrate or not. So it is carbohydrate, well defined. I mean, fulfill the definition. Polyhydroxy. Three hydroxy groups are there and aldehyde group is there. So this is a polyhydroxycarbonyl compound. Okay. Now the second question is this compound belongs to D series or L series? So first you have to put number 1, 2, 3 and 4. This carbon is stereogenic, this is stereogenic, right? See, second last carbon, see, this is the last carbon in the proper numbering. So the second last carbon is this. See, this OH is on the right hand side, so this is what? D. This sugar, this is a sugar, so you can say D sugar, or you can say D, and 4 carbon sugar is, so this is also called tetrose, tetrose, right? See, uh, OSE suffix is used to general naming, for general naming of carbohydrates like glucose, fructose, mannose, galactose. So carbohydrates are in general named as a with the suffix "-ose", right? So this is a general nomenclature. So this, what you can write this? This is D triose, 3 carbon triose, 4 carbon tetrose, 5 carbon pentose, 6 carbon hexose. So this is also you can write this. This is D triose, D triose. So if you do not know the exact name of any carbohydrate, then in this way you can what write the general name of that compound. So see, this is a D sugar, or you can say D tetrose, means this sugar belongs to D family, right? And suppose that we have this structure like this, COH, OH, H, OH, H, right? So 1, 2, 3, 4. This time the second last carbon OH, it is on the right hand side, right? And one more change here we can do. right? So this is what L sugar, OH in the left hand side, so L sugar or L tetrose, right? So this is the D and L nomenclature, right? Or you can say L tetrose, or one more name you can write, L aldotetrose, and this or you can write D aldotetrose, right? So in this way you can name the, I mean, carbohydrate molecules. Now I am putting here a note that the natural sugar, when I am writing sugar means I am talking about complete monosaccharide, disaccharide, all kinds of sugar. So natural sugar is D sugar. Means whatsoever in the nature we are taking from the nature, from fruits or from uh, I mean plants, whatsoever sugar we are taking, that is a D sugar. See, in our body we have receptors only for D sugar, not for L sugar. So if you intake L sugar, it is useless and it will be excreted from your body from as a waste, right? Your body or I mean our body cannot utilize L sugar because we do not have receptors, and until or unless it is not absorbed to the blood through the receptors, it cannot be further oxidized and converted into a smaller molecule and energy, right? So only D sugar is the natural sugar, and this our system is I mean meant for this D sugar only, right? So L sugar. So this is the reason why you are taking glucon D. Have you ever, listen, glucon L? No, not, because this is not a natural sugar and this is not, utilized by human system. Okay, so natural sugar is basically D sugar, and if your sugar has three carbon, so tri triose triose for three carbon sugar, tetrose for four carbon, pentose pentose five carbon sugar, hexose six carbon, right? In your syllabus, six carbon sugars are there: glucose, fructose, right? So hexose means six carbon sugar are in your syllabus. And one more important thing, that D and L, right? Suppose that you have a D and its mirror image, although its mirror image is like, I am writing the mirror image of D. See, mirror image of D is this, and this is equivalent to L. So basically, D and L sugars, they are enantiomers. See, in this chapter, most of the chemistry all of you have already, gone through. nothing new, but only how to apply that chemistry here in the carbohydrate, that's I have to tell you. So D and L, they are, suppose that, that's why I have changed this here. So these two molecules, they are enantiomers of each other. So if any point of time it is asked D glucose and L glucose, what is the stereochemical relation between them? So D glucose and L glucose are the enantiomers of each other, right? Okay, this is one point. And see, uh, if your sugar is your compound carbohydrate molecule have aldehyde group, then it is called aldo, and if it has ketonic group, then it is called keto, right? So one example of keto compound, so keto group cannot be terminal. So suppose that this structure is given to you. Now tell me, what is the, general name of this compound? So first you have to put the number. This is 1, this is 2, this is 3, this is 4, and this is 5. So 5 carbon, so you have to write pent. Prefix you can add keto, and OSE, it is the common. So this is a keto pentose, and see, second last carbon, stereogenic carbon is this. So second last carbon is this. OH is on the right hand side. So this is what? D. So what is the name of this, general name of this compound? A is D keto pentose, right? So OSE is the common suffix for carbohydrates. D for this. Keto due to this functional group, and D is this, and pent 5 carbon. So by using all this, you can write the general name of this. And if you take mirror image of this, if you take mirror image of this, then you will have CH2OH, CH2OH. These are not stereogenic, so hardly matters for us. So this OH, H, OH, H. So what is the general name of this? General name of this is L keto pentose. L keto pentose and D keto pentose. This is D keto pentose, and these two are enantiomers. These two are enantiomers. Enantiomers, right? So this is the, general D and L nomenclature for carbohydrates and general classification. Now see, in your syllabus, D glucose, this is aldohexose, D aldohexose. What is the molecular formula for this? The molecular formula for this is C6H12O6. And see, if you clearly examine this molecular formula, so this molecular formula belongs to D-glucose. D-glucose. This is also the molecular formula of D-fructose. This is also the molecular formula of D-mannose. And this is also the formula for D-galactose. See, so how to differentiate them? This is very important. This is very, very important. Glucose, fructose, mannose, galactose, D series all have same molecular formula, but different orientation of OH groups. Different may have different functional groups. See, this is keto sugar. Fructose is a keto sugar, keto, and all are aldo. Rest all are aldo. This is aldo. This is also aldo, and this is also aldo. Right? And all these, carbohydrates are in your syllabus. Right? So you must know clearly that what is the difference. All have same molecular formula. See, all have same molecular formula, C6H12O6. This is the common formula for all these sugars. So see, uh, I'm going to give you the trick or idea how to remember the structure of all these compounds. I mean giving you the structure of glucose. You all of you just remember the structure of glucose, and after knowing the structure of glucose, in addition to that, if you know a little bit concept, then you can very easily make all structure of all the rest three compounds, and you are able to differentiate between them chemically, right? For non-chemistry people, all this molecular formula all have carbon, hydrogen, oxygen, all have 6 carbon, 12 hydrogen, 6 oxygen. What is the difference? But all differs with respect to their properties a lot. See, D-fructose, this is the sweetest sugar. Highest degree of sweetness is there in the D-fructose, known so far, right? In honey, natural honey, basically fructose, that is fructose rich, right? So the sweetest sugar is D-fructose, although have same molecular formula, right? Same molecular formula, but in if you compare, the sweetest sugar is fructose. So see how to remember the structures of all these. First, you have to remember the structure of glucose. Glucose is a aldo sugar. So C double bond O. C double bond OH. CH2OH. See, this is the perfect structure of D-glucose. D-glucose. D, because this is in the right hand side in the Fischer projection formula. This is carbon number 1, this is carbon number 2, this is carbon number 3, this is carbon number 4, this is carbon number 5, and this is carbon number 6, right? So there are 6 carbon, aldohexose. This is glucose is aldohexose, right? And this is D-glucose, right? See carefully. If you have changes this OH from here to here, this is not glucose, this is something else. If you change this OH from here to here, this is not glucose. So see, if this OH turns from this side to this side, or its mirror image, if you take its mirror image, that is enantiomer, that is L-glucose, right? If you take the mirror image of this, then you will get L-glucose. And this L-glucose is not utilized by human system, only D-glucose, right? So this is the structure of D-glucose. How to draw the structure of D-fructose? Remember, this is a keto sugar. So what will happen? Do one thing. First, adjust the keto group. So keto group cannot be terminal. So CH2OH here, CH2OH here, and now keto group is here. Now see this part 1 and 2. Rest part is same for fructose. Now, so if you have the idea about the structure of glucose, then you can very easily draw the structure of fructose. This is D-fructose. D-fructose, right? So what is the relation, stereochemical relation or any relation between this? So D-glucose and D-fructose, D-glucose and D-fructose, they are functional isomers. Functional isomers. Because connectivity is different, right? So they are functional isomers, right? Okay. So this portion only is different between glucose and fructose. 1, 2, 3, 4, 5, 6, right? So only this portion. The rest part is same. This is the only difference between D-glucose and D-fructose. Now, before going to detail of D-mannose and D-galactose, I would like to define one technical term that is known as epimers. See, in carbohydrate chemistry, except carbon number 1, see, this carbon here, so except C1 carbon in aldohexoses and C2 carbon in ketohexoses, So any isomer related to this carbon number 1 in aldohexoses and any isomer related to the carbon number 2 in the ketohexoses, except these two, any isomer with respect to any other carbon is known as epimer. So except carbon number 1 in aldohexoses and carbon number 2 in ketohexoses, the isomers Isomers are said to be epimers. Epimers, right? See, in aldo hexoses 2, 3, 4, 5 are left, and here 3, 4, 5 are left, right? So these are, I mean, epimers, right? Now, I'm giving you one point. Mannose, D-mannose is 2 epimer of glucose. 2 epimer of glucose. Now see, very easily, now you can remember very easily the structure of mannose. It is the 2 epimer of glucose. So it means at carbon number 2, the orientation of OH is different. It means you just orient this OH from this side to this side, keeping other orientations same, you will get the structure of mannose. See the difference. Only orientation of one OH is different. So if only one orientation of only one OH is different, then they are said to be what? Epimers, right? So now you are able to draw the structure of what? Mannose, D-mannose. C double bond OH, CH2OH, OH, 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 and just orient. So see, this is the second last carbon. 1, 2, 3, 4, 5, 6. Second last carbon on the right hand side in the Fischer projection formula. So this is D series member D, and this OH at carbon number 2, it is different from the glucose. So this is a D-mannose. D-mannose, right? So D-mannose, it is the 2 epimer of glucose, right? It is the 2 epimer of glucose. Similarly, D-galactose, D-galactose, it is the 4 epimer of glucose. So it means at fourth position, the orientation of OH is different. So now you can draw the structure. The rest part is same. CH2OH, COH, OH, H, so at fourth position, the orientation of OH is different. See, so this is D-galactose, right? This is D-galactose. So if you remember thoroughly your this structure of glucose, then you are able to draw the structure of mannose, galactose, and fructose, right? So this is the way how to draw the structure of different monosaccharides which are in your syllabus. This is also in your syllabus, this is in your syllabus, and these two are also in your syllabus. So this is the structure of glucose, fructose, mannose, galactose, and mannose and galactose, and now you can draw the structure of their D series D members as well. You just take the mirror image and you will get the L series, I mean members of the compound, right? Now, see, this is homework for all of you. See, classify each of the following carbohydrates as an aldose or ketose and then insert the appropriate term to indicate the number of carbon atoms present. So this is homework, right? And one more thing, suppose that if it is asked to you some example, ketotriose, ketotriose. So if someone asks, okay, give some example of ketotriose. So this is very important compound, ketotriose, because you know three carbon carbohydrate with one ketonic group. See this. This is a ketotriose. And aldotriose is this glyceraldehyde. This is the aldotriose. Aldotriose. This is aldotriose. Oh, sorry, this is tetrose. This is aldotriose. So this has one stereogenic carbon, optically active. But you know this ketotriose, I think this is the only sugar in the whole sugar chemistry. This is the only sugar which is optically inactive because it has no stereogenic center. But it is a sugar because it satisfies the definition of carbohydrate polyhydroxy ketone. So polyhydroxycarbonyl compounds, they are known as carbohydrates. So this is a carbohydrate. So I think this is the only carbohydrate, hydrate, which is optically inactive, right? Ketotriose. And if you want to write the name, this is dihydroxyketone. Dihydroxyketone, right? So this is the simplest ketotriose and which is optically inactive. Now see the classification of carbohydrates. Classification of carbohydrates. Carbohydrates. See, this classification is based on, this is based on hydrolysis and hydrolytic product. Hydrolytic product, right? So this classification is based on basically hydrolysis and hydrolytic product. See, first one is the monosaccharide. Monosaccharide. Monosaccharides, they do not hydrolyzed. Do not hydrolyzed. Like D-glucose, D-fructose, D-mannose, D-ribose, etc. So these are monosaccharides. They do not hydrolyzed, right? Now second is oligosaccharide. The oligosaccharides, they hydrolyzed and produces 2 to 10 units of monosaccharide. Monosaccharides, right? For example, sucrose, maltose, lactose, trehalose, etc. So I'm writing those compounds mainly which are in your syllabus, right? So these are the oligosaccharides. Now, third one is the polysaccharide. Polysaccharides hydrolyzed and produces and produces more than 10 produces more than 10 units of monosaccharides. Monosaccharides, right? For example, starch, starch, cellulose, etc. Right? So this is the classification. Now let's see the example. See, sucrose, some examples of disaccharide, and this is in your syllabus. Disaccharide, right? Sucrose, sucrose, also called table sugar, also called invert sugar, invert sugar. Has the molecular formula C12H22O11, right? And uh, lactose and maltose, lactose, maltose, they also have the same formula, same molecular formula, C12H22O11, right? So all lactose, this is also called milk sugar, maltose, malt sugar, and sucrose, all three have same molecular formula, C12H22O11, right? But all are different because they have different monomeric units, or different orientation, or different isomers involved in these disaccharides. All are disaccharides, means they on hydrolysis produces 2 moles of monosaccharide. Now see, sucrose, plus H2O. Here, either you can do enzymatic hydrolysis, so invertase enzyme, or you can do chemical hydrolysis, you can put acidic hydrolysis. So you will get C6H12O6, 1 unit of glucose plus C C6H12O6, 1 unit of fructose. So glucose and fructose join together in a specific manner to produce sucrose. Similarly, see maltose plus H2O. Maltase or H plus, so glucose, see glucose plus another unit of glucose, C6H12O6 glucose, right? Now lactose plus H2O, lactase or H plus, 2 units of C6H12O6, 1 unit of glucose plus C6H12O6, 1 unit of galactose. Galactose, right? So glucose plus galactose is the lactose. Glucose plus glucose is maltose. Glucose plus fructose is sucrose, right? Now see starch C6H10O5 whole N. This is starch plus NH2O, H plus C6H12O6 glucose, right? So N molecules of glucose we will get here. So this is a polysaccharide. So this is polysaccharide, and these are the disaccharides. So this is the classification of carbohydrates, and I have focused only those carbohydrates, and basically these are the important carbohydrates, those which is kept in your syllabus, right? Now one more thing, if you see the structure of glucose, so this is the structure of D-glucose. So how many stereogenic carbon are here? 1, 2, 3, and 4. So how many optical isomers? So total number of stereoisomers, stereoisomers is equal to 2 to the power n. So 2 to the power 4 is equal to 16. So D-glucose, you have total 4 stereogenic carbon here. So accordingly, in D fructose and other cases, you can calculate the, I mean, number of stereoisomers. How many pairs of enantiomers you will get? Just by two, right? So you will get the number of enantiomeric pairs. Like that, you can calculate, right? N is 4. So this molecule cannot be divided into equal halves. So what formula I have given you, you can use that formula, right? So total stereoisomers 2 to the power what? N 2 to the power 4 for glucose. Similarly, you can calculate for other molecules as well, right?